Hi everyone. Let's move to the next great speaker, and I name Alexandru Bolboaca. Alexandru is a polyglot programmer, is a trainer, is a coach, and is the CTO of Mozaic Works, the company which is sponsoring this event. As you might guess, he's working closely with Adi, they are brothers, and I heard the first time about Alexandru when I read the guide that he wrote with Adi about hosting and facilitating code retreats, which was a really great guide. And today, Alexandru will show you a sweet way to refactor any code by using pure function. So taking from functional programming and how you can use these advantages to make existing code simpler. So without further ado, Alex, you're up.
Thank you, Nicolas. It's great to be here, and I will try to be as brief as possible, just so that we can have some conversations and not delay the schedule too much. And I think it will be very interesting to see what your reactions are to this method of refactoring legacy code, which I'm proposing. This is a new method that I'm proposing, and it's still under development. It's not something that's completely clear and obvious, and I have all the answers yet, but it's still very interesting to see if we can together figure out better ways of refactoring legacy code, which is something that we really need. Okay, so let's move on. As Nicolas said, I'm Alex Bolboaca. I'm CTO trainer and coach in Mozaic Works. I've done a lot of programming for the past 20 years in multiple programming languages. I started in C++ and recently went back to C++, and this is why the examples from this talk are in C++, but it's not really specific to C++. And then I moved to other programming languages. So let's just jump into this. So I'm gonna go through a few ideas, and you can already find the slides on SlideShare if you just clip this or write down this link. This is where you'll find the slides. First of all, I'd like to start by making just a quick introduction. Well, not necessarily introduction, more of a grounding of the problem. What the problem is legacy code. And I believe the first problem that I saw whenever I work with teams and try to help them is that legacy code is everywhere. And I guess people who presented before me have already discussed about this, so I won't go into many details. You know the problem. We have legacy code everywhere. But what's more sad from what I see is that usually legacy code erodes the will of programmers. So we have people who really want to learn new practices. They want to learn how to do test-driven development or unit testing or refactoring or write clean code. And then you try to learn these things and you go back into production and they don't fit anything that you have there, because it's so hard to change all the code such that you can apply these techniques. And in time, this leads to very unhappy people who believe that, we cannot change anything and it's hopeless and so on. And so we discussed about legacy code. Michael Feathers says any piece of code that doesn't have automated tests. Personally, I prefer to think about any piece of code that you are afraid to change. And I've heard earlier another definition, which I like even better, which is code that has value, actually provides some useful value, but you are very afraid to change. And the problem is that, legacy code leads to the dark side. At least this is what I saw in practice. I saw, we are afraid to change things. This leads to anger, this leads to hate, and this leads to suffering. And personally, I would like to have less suffering in the world of programmers. And I'd like to look a bit at the existing methods that we use for changing legacy code. And when I talk about legacy code, the main problem is when we are trying to change things, when we are trying to add a new feature, perhaps write it in a better way, when we are trying to fix a bug without creating 10 other bugs, when we are trying to do something that is actually useful for a business or for the product. And so we have a few existing methods, and the first one that I see very, very often is the change and pray method, which is basically, I'm going to make this change and then pray it works. And this is great if it works for you. I have no idea how you're doing this. And the problem with this is it's not repeatable, it's not transferable. I don't think you can teach other people how to do this and do this effectively and repeatedly and work and so that it works. And so we end up with another method, usually when a manager comes in and says, okay, stop changing that code. Whenever you change that code, something bad happens, so stop changing it and freeze it, right? We don't touch that code anymore. Which is actually, it's not such a bad method, and it can work with a strangler pattern, which we'll discuss in a moment. But it's also not necessarily helping. It turns this code, this part of the code in inventory into something that you cannot develop anymore. But it reduces the risks a lot. And so when I say this is it works quite well with a strangler pattern. A strangler pattern is a way of dealing with legacy code, which is quite effective when you basically start to replace and actually write all the new functionality that you want to add, not in the legacy code, not by changing that part of the code that you are afraid to change, but in a separate part of the code that you are perhaps writing with more modern things. At least you can have tests or follow some solid principles. I don't advocate for completely changing the technology or the techniques that you are using because there's a learning curve there, but perhaps you can improve a few things or take something that you learned from the existing code and make it better in the new version of the code. But instead of rewriting everything, you start by basically adding a facade and then redirecting the calls to that facade to the old implementation or to the new one. And then in time, and when I say in time, it can be a long time, you grow the modern thing and you reduce the legacy thing until you end up with a modern implementation. And this is something that is perfectly effective. It works fine, it reduces risks. Of course, there are some interesting challenges there. What if you really need to change some of the legacy code when you add new features and so on? But it's quite an interesting way of dealing with legacy code. The other method that we know is, of course, Michael Feder's method, which basically, it's more complicated than that, but it basically says we identify seams, we do some safe refactorings to exploit those seams, we write some characterization tests on those seams, helping ourselves from those seams. And then once we have the tests that characterize the existing code, we refactor to the desired design. This is an amazing method. It's very good in the sense that it gives results. It's safe. You can do it. However, we'll see that it requires a lot of skill. But before that, I like to quickly mention Mikado method, which is another method, and I saw there was some demo earlier. If you don't know about Mikado method, there's a book about it. It's really useful for dealing, especially with the type of code where you try to refactor something and something else breaks, or when you try to go into one way, and then you realize that you need to change in multiple places. So the specific problems are usually best fit for this method. The types of problems where you try to start refactoring, but then you get tangled into the mess. Now, the problem with all these methods is often you cannot use only one method. You need multiple methods, and you need to be a bit imaginative about what you use, and you need to know those types of methods. The biggest problem that I have is that they are very time consuming. Every one of these methods, it takes a long time whenever you are working with really tangled and difficult code. And also they require a few skills that are multiple skills, also rare skills. And I wrote here a list of how to identify and abuse themes, how to write characterization tests, and so on. But from my perspective, what I saw as the biggest problem is it's a problem of imagination, because you need, whenever you deal with legacy code, you need to figure out strange ways of abusing themes, basically. And this is probably the hardest thing to do, because you need a lot of imagination to figure out in some context how to do it. And then it's also a matter of, when you start refactoring things little by little, you need a certain type of imagination to figure out that, this method where we apply extract and override will actually turn into a mock, or can be turned into a mock at a later time, which means we'll have a dependency there so we can have an interface. It's kind of difficult to imagine these things. And that's what I saw as the biggest hurdle whenever I try to work with random developers on refactoring their code. I'm sure there are professionals, and I've met quite a few of them, who are very happy to do that and have the right skills and imagination and so on. But the truth is, we are few, and there's a lot of legacy code. It also requires months, maybe years of practice. So all of us who can do this effectively have gone through, test-driven development, know how to write tests, know how to refactor effectively, and so on and so forth. But if you take some developer from a company and who's been developing in a certain way in a legacy system, and now we go there and say, okay, so now you need to learn unit testing and refactoring and themes and all those things, it's quite overwhelming, and it takes a long time. So because of that, I believe that we are now living with three choices. We can either live with a code that we are afraid to change and slow down development. This is a choice that many teams make. Refactor the code down safely, which is another choice that I see many teams making. And unfortunately, usually this ends up in failure. And by failure, I mean you end up with code that is not necessarily better than what you first have, but also has more bugs than you had before. Or use a safe method, which you need to learn and practice and apply. And it's a method that's quite slow. So then I'm proposing a new method, and this method takes advantage of a few things that I noticed from functional programming. And what I'm proposing is a method that goes in 3 steps. Refactor code to pure functions, and I believe that I can teach and I can identify a number of mechanics, probably 10 to 15 mechanics that you can use to do this. And at this point, you don't write tests. You mechanically refactor code to pure functions. Second step, write data-driven or property-based tests on these pure functions, which should be very easy because they are pure functions, and we'll go into details of what they are if you don't know. And then refactor pure functions to classes or something else. And this is something that's interesting because, for example, when you think about data transformation between different types of data, let's say you want to get, I don't know, an RSS feed and turn it into a CSV file or something like this. Usually, whenever we implement something like this, one of the common patterns is to go through a intermediate step, which is kind of a nominal format for the data. It used to be an XML type of file, but now perhaps it's something different. And that allows you to control kind of the middle part. And what I'm proposing is that using pure function is kind of the nominal form for design. So let's see first, discussing the first step, what is a pure function? And the definition of a pure function is a function that returns the same output values for the same input values. So whenever you pass input values with specific values, what you get out is the same output value. It does not depend on state. So let me give you an example. Again, this is C++, but the examples are simple. You can probably read them even if you don't know C++. If you don't know C++, one important part is the const in front of the parameter that says that you cannot change the parameter inside the function. So what this does is fairly simple. It receives two integers, it returns an integer, it does not change any parameter, it does not depend on the existing state, it just gets values, returns values. An impure function would be something like this. And again, if you are not familiar with C++, what you have there is an int ampersand first. That means it's a reference kind of variable. You can change it when you do first plus equals second. That actually changes the first parameter, and when you return it, it's actually also changed. So, and this would be an example of an impure function, something that changes the parameter or the state that's around it. Now, an example of a pure function that I tolerate is, and that if you ask a functional programmer, they will not tolerate this necessarily, is something that does a local state change. I accept this because for my goals, it doesn't matter. If I can just remove all the madness of state change from my functions, then this clears up the code pretty nicely. And so if the state change is just local, I'm perfectly fine with that. I like pure functions because they are boring and there's too much excitement in software development. And so just think about your daily experience. When you go home and you turn your switch on, you expect the light bulb to start working, the light to turn on. You don't expect your water to start on your sink, or your fridge to open its doors or anything like that. We don't expect side effects in the real world, yet when we are doing programming, we deal a lot with side effects. So I like pure functions because they are boring, they have no dependencies, they are very easy to test, because basically testing them is a table. You have these input values, you have these output values. There is no state. I don't care about anything else. The interesting part then is, if you think of any program, no matter how complex it is, you can write it as a combination of pure functions and functions that do input-output. So if you can separate everything that, for example, in a web application, everything that reads the request, builds the response, everything that writes cookies or writes things in the session or writes to a database or to a file, that's input-output. Everything else that's inside of this kind of program can be written as pure functions. You don't have to do that. It's not necessarily perhaps the best structure for it, but it's important to know that you can do that. And once you have pure function, you can also move to lambdas, where you can take advantage of various operators. And what I like about this method, and where I think we have the biggest and the fastest, the biggest advantage in terms of speed, is that usually when we try to apply the Michael Feathers method of dealing with legacy code, when we write characterization tests, we need to deal with dependencies. When you try to refactor towards pure functions, those dependencies become explicit very quickly. And so the method that I try to propose is the following. Whenever you want to refactor to pure functions, by the way, whenever I deal with legacy code, I never start by reading the code, because if the code is simple enough that somebody can tell me what's going on there and it's not a problem, if the code is too complex, it means that trying to understand it by reading it will take me much longer than understanding it through other means. And so I like methods that are mechanical. And the method that I use here when I try to refactor to pure functions is simple. Pick a code block, extract a method from that code block, make it immutable. In C++, that's fairly simple because you started in consts everywhere, and then your compiler will shout, oh, that parameter is changed or that value is changed, and deal with those changes through a few transformations. Then I can make it static. Once it's static, I know it's not dependent on the class where it's in anymore, because again, the compiler will tell me, oh, it's using certain data members and so on. And finally, I like to, you don't have to, but I can replace it with a lambda, because when I have lambdas, I can combine them in interesting ways. And it's important to understand that this is just an intermediary step, and it's a pattern whenever we deal with legacy code, that in order to get to a better version of the code, we first need to go through an uglier version of the code. That's how it is. But we prefer safety in what we are doing over the niceness of design in the intermediate step. So let's take the example of trivia once again. You've probably seen this before. I'm just gonna pick one part of the code, which is this. Basically gets, well, I know the code, so I know it kind of creates pop questions. This is something that you can see by reading the code. But the interesting part is you don't necessarily have to read it. So I can extract it into a method, and I can use the IDE to do that, or I can use my manual refactoring steps for extract method, and I end up with this. And then what I can do is I've extracted the method, and it doesn't actually matter which lines of code you are using. You try to select a code block, extract method, kind of see what the IDE is telling you. Is this the right method or not? Does it have a lot of parameters? You get some information when trying to do that, and you try to kind of select a scope that perhaps makes more sense. Now, this is a simple example for the sake of it, but I've also tried this with more complicated examples. And then you try to make it immutable. So I have added a const keyword on the I thingy, and this doesn't lead to any compiler error. This means that nobody changes I. And the compiler is telling me this. Of course, I could read that, but I don't want to. I want a tool to tell me that. And then I try to make it immutable. So I make the next step in C++, I can make the function const, which basically means that it cannot change anything from the class, anything from the class it's in. And here we have, oh, compilation error, we have a state change. What can we do now? So now we've isolated the part of the code that is actually making a state change. Everything else can be immutable. First thing, I revert the change because I want to have everything working for as long as possible. So I'm back to the previous method. Now I can separate the pure part from the impure part, and I often use comments temporarily to see this difference. And then I can extract the pure function. So now I have a pure function and I have an impure function. And if you notice, you don't necessarily have to, let's say, completely understand or read fully the code, because everything that I've done until now has been given to me by the compiler. And now the next step, I can inline the initial function. So now I have a very cool thing. I've just separated a pure function without trying too hard, let's say. The create pop questions function. So now let's look at the pure function. This is how it looks now. We can simplify it a bit. This is the automated refactoring done by CLion. I can change it a bit, simplify, inline a variable, still const. Cool. And now I can transform it to lambda. And by the way, if you once again, if you don't know C++, the syntax for lambda is a bit weird. There's a square parenthesis in front of the function, which you can safely ignore. For now, I won't use it. But basically what it is, it says I go from constant I to a function that returns string. That's basically what it does. And now I can use this in my create pop question function. I can move the lambda up and I can inline the method. And now I have just separated completely one part of the code from the existing code. It's now out of the scope, and because it's a lambda, because it doesn't depend on anything from the state of the class, it doesn't depend on anything, it doesn't change anything in the state. I can move it anywhere I want, right? And that's the power of this technique. That's what I like so much about it. Cool. So this was just an example. So basically what I needed in order to do that were a few things. I needed to know how to extract the method. I needed to know how to inline. I needed to know how to change a signature, and I needed to know how to turn to a lambda. And the compiler will tell me what the function dependencies are. And I like that this is a very mechanical process. I like mechanical processes because they allow me to learn a few mechanics and to be predictable, and to not think too much about what I'm doing, because one of the hardest things when you are dealing with a horrible mess of a code is to keep track of everything that's going on there. And so in this manner, it's just little by little separating the pure part from the impure part. Okay, so the result is pure function, no dependencies. I can move this anywhere I want. It's a free kind of a function. Okay, now we have this was, let's say, an easy example. What about another type of problem? What if the function that we are dealing with makes a state change? So let's see what we can do here. We have this function, that has a number of state changes, and just for the sake of it, I've added some comments to see precisely which line in the function does what. So there's a state change, state change, state change, state change, and there's some input output. So I can now extract a method, this method that does a state change. And now what I'd like to do with the method that does a state change is to turn it into a pure function. What would a pure function have to do with changing state? Where the thing is, you can do something very interesting, which is you get the current state in, you get the new state out. And in the middle, you have the pure function, which just basically does the transformation. But I know where I want to go. I don't precisely, I also need mechanical methods to go there. And so what would be a mechanical method? So first I need to copy the initial value of players, do the modification, set the data member to the new value. This is something that I couldn't find a way to do automatically in an IDE. So basically I have to do this manually. Create first the initial value, just make a copy, modify the copy, and then set to the new value. And now I can extract the thing in the middle, kind of. I can have the add player pure here, which receives a string player name. It also creates like a vector of initial players, does the pushback, returns the new value. And as you can see, because it's a const parameter, it's a const function, it doesn't change anything. Now what I have is a function that is pure, separate from the function that is impure. And of course here, if you are a C++ programmer, you'll see that I'm copying a string, a vector, sorry, and that will increase the memory consumption and so on. It doesn't matter for now, we'll deal with it later. So in the end, what you end up with is something like this: set player name to players list, set player pure player name, returns the list of players. And we can inline that, and we end up with this. Our add method now has add player pure, uses add player pure to give the right, to create a new version of the player's vector. Okay, and then I try to make this static, and this is where we see a problem. Players unavailable. Why? Well, you may have noticed that it's a variable, it's a data member. I'm changing a data member, but again, the compiler is telling me that when I try to make the function static. Whenever I see this, first thing, undo the static. I want things to compile, I want things to work. And the next step is to introduce the parameter. So now I'm introducing the players there as the parameters. And finally, I can now make this static and move to a lambda, because I no longer use that, but I now need to receive two variables. So I need to receive the players, the current vector, and the player name, and I will receive a new version of players that includes whatever was before and the new player name. By the way, if you know about monads, this is a state monad, but you don't have to know about it. It's just quite easy to do by refactoring little by little. Once again, we inline the call, and we end up with players, set player name to collection lambda, player name players. Perfect. So we have just dealt with another big problem related to legacy code, which is change state. And we've done it in a purely mechanical way, just by going through a few steps. And I've added a new mechanic, which was, if you deal with a state change, you need to go first through copying the initial value of the state and then passing that into the function and then setting it back to your data member or whatever you were using for the state change. So where does this lead us? It leaves us with a list of mechanics, and this is a work in progress. We've seen for the first part, extract method, make const, make static, introduce parameter, turn to lambda. This is a list of mechanics that we can use in general. Then whenever we have a state change, we need to do this kind of dealing with state that I've showed you as a mechanic. And there are a few more that I found by practicing. For example, if you have an if-else thing, you may end up with the result decide. If you have just an if, that's when it becomes interesting, because you need to refactor this to an optional somehow if you want to get a pure function. Because a pure function needs to return a value, and if it's only an if, on one branch it will return a value, on the other branch it won't return anything, and that's why you need an optional thing. If it's an input-output kind of thing, you need to encapsulate basically the thing that does the input-output, and then you'll end up with output something or read something. Cool. So again, this is work in progress. I'm still trying to figure out better ways of dealing with this, but what I like is that we can do this with a very short list of mechanics. A few words about testing. I said that it's very easy to test pure functions. It's basically a data kind of test. I love a lot how you can do this in Groovy and Spock with a table exactly as it should be. But in C++ you can do you can use doc test, for example. You can also use property-based tests, which because I don't have a lot of time left, I won't go into. But the fundamental idea is, since you have an interval of values as inputs for your function, and it's a pure function, you'll get out an interval of outputs. So basically you can figure out some mathematical properties that you can test for. For example, if you are testing something like a power function, one property that we know from mathematics is that any integer to power 1 is the value. So then you can test for this kind of property, and this will cover much more values in a more general way than just testing for a table of elements. So you can combine these two. Now, the last step would be, we have these pure functions. Let's say we've extracted 10, 20 such functions. How do we get back to classes? Because unless you are a functional programmer, you probably want to get back to an object-oriented kind of design. And this is where we get to a very interesting equivalence. It turns out that a class is a set of partially applied cohesive pure functions. So let me explain this through an example. Let's say I have a class that has a player that has a name and a score, initializes as a print function, and so on. This is equivalent with two functions, print name, well, actually here one function, print name, that receives a name and just prints it out. And this is basically, you can do the same for the score, but for the score we don't have here a specific action. What this means is that we have if we have a lambda like this, we can actually encapsulate it quite easily and turn it into a member function by moving the name as a data member in the class. The print name becomes a function now. It doesn't receive name as a parameter, but uses the data member. And how do you identify those pure functions that fit together? One way is to look at names. If you figured out proper names for them, if you see print player name, compute player score, perhaps they need to be together somehow. Or similarity in parameter list, sorry. So if you have player name, player score, player name, player score, perhaps those two things want to be together somehow. So then, if you see these types of things, you create a class, you move the functions into the class, the common parameters become the data members, you're the constructor, but now you also have tests because you've written them. And those tests can easily translate and be refactored to by adding a few setup steps to work for your new class. So, in conclusion, what I believe is that this technique, again, I'm still working on it, but I believe it can be faster to learn. This was my primary goal. I want something that is mechanical, but something that I can teach developers so that they can deal with the reality of the existing code that they wrote or other people wrote. And I believe we can split this into perhaps 20 mechanics that you can practice in a safe manner on simple examples and then on more complex examples, but outside the production code, and then go into your production code and actually be able to apply that. I like that it's faster to refactor because I'm using the compiler, I'm using the existing refactoring tools to eliminate the dependencies. And this is the hardest problem when dealing with legacy code. I can write tests easier. It's awfully hard whenever you have a complex legacy code. Usually writing the first test can take hours or even days. I've been through that. In this case, I can start immediately and then write tests that are very, very easy. And later, it's safe to refactor to classes. Now, I've seen a few problems with this. One is that you have to be very careful to introduce unexpected side effects. Temporal coupling can be a problem if you have a function that needs to be called after another function or before, and you extract one of it, and then it becomes, you can go all the way to lambdas without quite noticing the temporal coupling. And there are issues with global state. If you don't notice global state, you can have global state in a lambda perfectly fine. You still need discipline and practice. It does not solve all the problems. And one interesting thing is that when you are doing this, the resulting design doesn't follow tell don't task. If you need that, then you will need more refactoring afterwards. Right. So that was it. I have a codecast, first episode on our Think Design Work Smart YouTube channel. If you search for it, you will find it. We also have a video, Pure Functions as Nominal Form for Software Design, which is something that explains more this idea. And the thing is, with the codecast, I want to record more episodes, but due to the pandemic, I have to stop and do something else. But I will, as soon as I can, I will start recording the next steps. But you can see the method in practice already up to a certain extent. That's all. If there are any questions, I'd be happy to answer.
Nice, thank you. Do you want me to read the questions for you, or do you have access to Crowdcast?
I have access to Crowdcast. Let's see.
I can give you the questions.
Yes, let's do.
So, thank you very much, by the way, because it was really interesting. It's an approach I've heard about, like I heard you mention it, but I never got into the details. So it was really interesting. The first question we have is, could you give an example of how sims are abused, as you mentioned?
So let me see. I'm trying to remember something that we did. Well, what I mean to say is that first of all, you need to know the types of sims that you can find, and then you need to figure out where to kind of open up those sims. And this opening up of sims is what is basically kind of an abuse, right? That's what I mean. And what I notice is that many developers have trouble, even if you explain the concept of sims and so on, they have trouble figuring out, okay, so where am I now? What do I need to do? This starts getting very, very confusing very early. So I don't have a specific example, but even if you think about something like extract and overwrite, like a very simple kind of method for opening up a sim. First of all, you need to figure out kind of what the part of the code you need to extract. Let's say you just extract a full function, you extract and override. Then what I noticed, developers already get confused between the override and the copy and let's say the real code that is still working, but also the override is there just for the tests. And it's already getting quite confusing. So that's kind of what I'm trying to hint at. And I know if you have a lot of practice, it's not confusing. If you know about mocks, it's not a problem. But imagine you don't know anything about mocks, you don't know about testing, and somebody comes and tells you, let's do this strange, weird technique. It's not normal programming.
Yeah, but again, I do have an example in mind because you have different kind of sims, and if you take a language like JavaScript, for example, you can have very clever hijacks of the import system to hijack what is the code that you actually import, which works, but it's definitely not boring code at the end.
And actually you can do the same in C++ because if you have libraries, basically in C++ you include a .h file. And you can include a .h file and write a CPP file that matches your .h file and compile with that. And that's again something that's weird. We don't do that all day.
And it can lead to very tests that are harder to maintain afterwards. So yeah, definitely. So second question, is any function returns a value and doesn't change the state in Java be a pure function?
So in Java basically you don't have the constants that you have in C++. This is one thing that I'm missing when I do Java. So basically what you can do is to make the function static and see if it changes anything from the class, any data member. But then you need to pay more attention to the change in parameters, if any change has happened in parameters and so on. But yes, the definition is the same. A pure function is a pure function no matter the language. A pure function is a pure function, and for the same input values you get the same output value. That's the definition. And you don't change the state surrounding it. So there are different ways of achieving this in different programming languages. but the definition is the same.
Nice. Thank you very much. Yeah, that's it. That's all the questions we had. So we're good. Thank you very much, Alex, for this. And I think we're going to take a short break and move up to Woody's talk.
Thank you.